Hello all. We will have today a short review of basic knowledge about DC to DC converters and especially the switch to ones. We can distinguish two categories of DC to DC converters. We are talking about the linear ones and the switch to ones. Actually, the switch to ones were invented to outcome one of the drawbacks often encountered while using linear regulators. And we have here an example that will tell you about what it is. So imagine we have a car, we have a car battery of 12 volt, and we have an electronic device in the car that needs to be supplied with 5 volts and consumes 2 amps. So we have to provide a total power of 10 watts. Well, in this case, if it will be to use a linear regulator or a linear DC to DC converter, we will have such a linear regulating element, which is Q2 in our case. So we will see that, or we can see that on one hand we have the battery voltage, which is 12 volts, and on the other hand we have the needed 5 volt at the output. That means that the difference between 12 volt input and 5 volt output needs to be across this regulating element Q2. And if we know that the entire 2 amps current that is supplied to load has to pass to this Q2 because there is no other way, that means in this process we are dissipating in terms of heat 14 watts of power. So we are transferring to the load 10 watt. We are dissipating 14 watt on Q2. So in total, we are consuming 24 watts from the battery. So the biggest problem, as you can already imagine, it's about the efficiency. So we are providing 10 watts to the load, but we are consuming 24 watts. So we have a very low efficiency, like 41, 42%. Okay, so that was the main reason why switching regulators were invented in the end. So it was needed a more efficient way to transfer the energy to match the different voltage levels. Okay. There is another point related to the volume and in the end the cost, but this was the efficiency point was the driving force, to say like this. Okay, so switching regulators or switch to DC converters, we have three basic topologies. We have the step down or buck. For this one, the output voltage is all the time smaller than the input voltage. We have the step up converter or boost. In this case, the output voltage is all the time higher than the input voltage. And of course, we have the combination of both, which is buck boost, for which the output voltage can either be smaller or greater than the input voltage. We often use three-terminal PWM switch model, which was developed by Vachev-Orperian. The idea is that all those three basic topologies are presenting discontinuities because of this switching behavior, turning on and turning off of a MOSFET. And we have switched current waveforms. So in principle, we have a system with discontinuities. And the basic idea was to generate an average model and to replace this switching network identified here, for instance, by the MOSFET M1 and the freewheeling diode D1. So replacing this switching network with this average model so that the system can be linearized, and then the standard solving techniques of linear time variant systems can be applied. We will see later on how this can be used. So this three-terminal PWM switch model, actually, it is called invariant because the equations involved here are not changing regardless of the topology it is used. So it is therefore a very convenient tool when it comes to analysis of switching regulators. Okay, operating modes. We have what is called continuous conduction mode. In this case, the inductor current waveform never reaches zero within one switching period. Then we have a particular case which is called boundary conduction mode. That means during one switching period, well, the current starts from zero, and then rise up to a certain level, then goes down to zero, and at the time instant when the inductor current reaches zero, at the same time instant, a new switching cycle is initiated. So this is as I said, a particular case. It is actually the transition between continuous conduction mode and discontinuous conduction mode. Discontinuous conduction mode is, of course, the current starts from zero. The current in the inductor we are talking about goes to up to a certain level, then goes down to back to zero, and then there is also a time interval in which it stays there at zero. So on a visual inspection, you can see, or you can identify, okay, in continuous conduction mode and boundary conduction mode, the system or the switching regulator has two operating states, yeah, more or less two operating states, while for discontinuous conduction mode, there are three operating states. Yeah. Okay, so what is to remember here is that the current waveform in the inductor gives the operating mode, CCM, BCM, or DCM. There are three important principles used in the analysis of switching regulators, and these are, so when we talk about steady state in principle. So in steady state, we have inductor volt second balance. That means the average voltage over the inductor for one switching period must be zero. Otherwise, we are not in steady state. We are in a transient condition. In a similar manner, we have capacitor charge balance. So that means the average current through a capacitor over a switching period must also be zero. If for instance, if this is not, imagine if we have an output capacitor, if we put more electric charge in that capacitor than we extract over one switching period, the effect will be that the voltage over the capacitor will start to rise, right? So that means we are not anymore in steady state analysis. Normally, when we talk about a regulator or a voltage regulator, we want to have a fixed output voltage. Yeah. So capacitor charge balance must be also satisfied at the same time. We need inductor volt second balance when it comes to steady state analysis. We also use the small ripple approximation. Small ripple approximation. For instance, we know that the output voltage has a certain ripple, but the AC component, I mean the ripple, is very small in comparison with its DC value. Therefore, in the analysis of DC to DC converters, we often consider the voltage as being constant over one switching period. Okay, so those are the three very important principles used in the analysis of DC to DC converters. As you noticed from the basic topologies, um, we are dealing with inductors and capacitors. Those are energy storage elements. Of course, we can calculate the instantaneous power simply by the product of voltage and current through them. And if we want to calculate the amount of energy that is stored in an inductor or a capacitor, we just simply need to integrate the instantaneous power. So in the end, we will have something like energy stored in an inductor would be inductance values times the um, squared current at the time instant we are referring to over 2. And similar for the capacitor, the energy stored in a capacitor is the capacitance value times the voltage across the capacitor at the specific time instant squared over 2. We will, of course, discuss or have to deal with transfer functions especially when it comes to the AC analysis of switching regulators. And we have a generic transfer function h of s. It can be defined as a ratio of two polynomials, n of s and d of s. N of s is the numerator and its roots are called zeros, and d of s is the denominator and its roots are called poles. So we will deal with poles and zeros in our AC analysis. Of course, we will use Bode plots to have the gain and phase characteristics. So for this reason, we need to compute the gain and the phase. The gain is simply the modulus of h of s, which is in the end the root square of squared real part plus squared imaginary part, and the phase is simply the arctangent of the imaginary part over the real part. We will need to discuss also about some stability criteria. So in general, we will talk about the cutoff frequency, which is the frequency at which the gain characteristic in a Bode plot hits 0 dB. We will talk about the phase margin, which is the amount of phase above minus 180 degrees at cutoff frequency, and we will also talk about the gain margin, which is amount of gain that is lower than 0 dB when the phase hits minus 180 degrees. And in general, as stability criteria, we are looking, because we have closed loop systems. I mean, we are looking for a certain slope when it comes to when we are referring to the gain characteristics. So we need to have a slope of about minus 20 dB per decade at 0 dB crossing or at cutoff frequency. We want to have a phase margin, I don't know, more than 45 degrees or 60 degrees depending on the application, and of course we would like to have a gain margin around 10 dB. Okay, so those about the stability criteria. Thank you for for watching. This is all for this very quick review of basic knowledge in regards to DC to DC converters. Goodbye.